Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are going to discuss one more elimination method. We are discussing chapter 5, one-dimensional minimization methods. So this method is known as interval halving method. Okay, so in this method, exactly one half of the current interval of uncertainty will be deleted. That is why it is called interval halving method. And also, it requires 3 experiments. Basically, in this book, they're calling X1, X2, X3, X4. These values are actually they're calling as experiments. So in the first iteration, we have to, or in the first stage or first iteration, we have to take 3 experiments. In first iteration. And in the consecutive iterations, we'll have 2 experiments. Because of the procedure, one of the point will always be remaining from the previous stage, the previous iteration. So 2 more is needed. So that is why we call it 2 in the successive and second and continuous iterations. So basically, even though we are going to use 3, but 1 is already available from the previous one. Method is simple. First of all, an interval is actually equally divided into 4 parts, starting from A to B. So middle one we call x0. Then we have x1 and x2. If you have to find the function, so 3 cases possible. Case 1, if we have this scenario. So since a unimodal function, only one minimum and maximum is possible. And as you can see here, that minimization is occurring in this direction. So you can exactly discard half of it. Okay, so half of the portion will be discarded. Okay, so next possibility is this. Now we're talking about the decisions. So how we are going to take the decisions. So again, x0, if we have here x1 and x2, then, and if this is the scenario, the maximum value is here, then smaller. And since it's a minimization problem, we eliminate this portion, this half. And what will happen in the third case, that is in between A and B, if you have x0, x1 and x2, and if you have these 2 values to be equal, in that case, in the middle is a smaller value. Okay, so this is what we have. So in this case, we have to eliminate these 2 values. So this is the decision. We can also check after each interval whether the condition of exact values is fulfilled or not. So the values of the L after each iteration, that is after that is B minus A. That value is whether it is smaller or equal to a certain minimum value or exit value given, which is represented by this epsilon. So if this condition is verified, then the convergent criteria is satisfied, and this is, we have to stop the procedure. Otherwise, with this L, we have to go to the next procedure again. So if in the previous case, we try to derive the formula using n to be is number of iteration. In the previous case, that is dichotomous method, but now the n was number of iteration. But in this book, they are trying to make assume that n is actually number of experiments. So the previous formula that we have derived, n ln equal to basically L0 by 2 to the power n plus del 1 minus 1 by 2 to the power n. So if n is iteration, then this formula is okay. Otherwise, if any k is basically your number of experiments, then the formula for the dichotomous search will be basically just this n will be divided by 2. Okay, so 2 to the power n by 2. So this is slight correction, whether you take n equal to iteration or n equal to number of experiments. How many you're taking. In the previous case, in each step, actually, you're taking 2 experiments. And here, in this method, in the first stage, we are taking 3 experiments and the subsequent 2. So your value of the formula for ln, the derivation is not given, but it's actually it is inherent. You can experiment with this one, 1/2 of n minus 1 by 2 L0. So this will be your interval of uncertainty after experiment. So in the first case, experiment has to be 3, and the rest of them experiment has to be 5 or 7, because we are just increasing by 2. So the condition given here is n greater or equal to 3. So as you can see, if you set n equal to 3, we're going to get ln is equal to L0 by 4, which makes sense because initially we are dividing into 4 equal parts. Now, what will be the next one? Say we discarded this portion here. This portion is discarded. Now, the next portion that we have here, already the middle one is already there. So what are our objective? We can just find the middle of this one and this one. Okay, so we can also call this one as new A, this is B, and this is your new X0. Similarly, this will be your new X1 and X2. So gradually, every values you have to pick. So for simplicity, you can also keep the values, otherwise you are going to get confused. So X2 will be there, and just term this is X3 and X4. So let's see the problem that we have solved using the dichotomous search method. Let's use the same. Let's try to solve the same problem with our interval halving method. So first, let's see how many steps we have to go with the formula. So we know that our 10% exact value, and so the function is same minimization problem, x minus 1.5, and our initial inverse 0, 1, and our 10% exact value. So method is different. So method here is interval halving method. So first thing first, so criteria that is given. So half of ln by L0 has to be lesser than equal to 10%. So ln is the formula that is given here, half ln also have half of n minus 1 by 2 into I0. You also have I0 here, so I0 is 0 getting cancelled out, or I0 is basically 1, so you don't have to worry too much about it. Let's say then 0.1. If you solve it, then you're going to get the values of n. Okay, so n has to be greater or equal to 5. So since n is the odd number, so n has to be 7. So 7 means how many iterations you have to go for. So in the first iteration, iteration 1, you need 3 experiments. And iteration 2, you need 2. And iteration 3, you need 2. So basically we have to go up to 3 iterations. So let's start with the first iteration. So first iteration exactly. So the interval L0 is, or LAB is, in the first case is 1 minus 0, so basically 1. So equally, if you divide into 4 segment, okay, so where your AO is 0 and B is 1. So if you equally divide into 4 segment, then your X1 value has to be 0.25. X0 has to be 0.5. We assume that in the middle we have the optimum point, so that is why we call it X0. Then your X2 is 0.75. Next step is to find out the function value f1 is 0.25 into 0.25 minus 1.5. So this is minus 0.3125. F2, we're not putting the value, we just do it, minus 0.5. And F3 will be minus 0.5625. So plot the values 0, 1, middle 0.5, which is your x0, 0.25, and 0.75, x1, x2. Actually, you should have drawn it up because you have the negative values. So let me use a different color to denote that. Okay. So now what you can see, which is the minimum one, is this one. So this is minimum. You have this value and you have this value. So according to our criteria discussed earlier, we have to discard this portion. So our new interval will be, since f1 is greater than f2 greater than f3, so our new interval will be from 0.5 to 1. So from 0.5, there is x0 to 1. So this was your A, this is your B. So new interval is, you can also create AB again. New interval is 0, 0.5 to 1. And also in the middle, x0 is already there. So you can take the same notation as the book has been doing. So we're calling this as A, which is 0.5. This is your B, which is 1. and this is the middle is your x0, which is it's better to draw it. X0 is 0.75 exactly at the middle. Then your x, one half of it is your x1 is 0.625, and your x2 is 0.875. So two more experiment is added. Now our values we already calculated, just half the middle points to make it equally divided into 4 parts. So 0.625, 0.75, and 0.875. The corresponding values of F1, F2, F0, and F2 are basically minus 0.54685, minus 0.5625, minus 0.5589594. Okay, so which one is smaller? So if you plug the value in the middle, we are actually having the smallest value. Then we have slightly higher value here. Hence, also this will be the case. So under this circumstance, we actually have to eliminate these two sides. Okay, so this portion will be eliminated because our minimization point is minimizer, or minimization point is actually in the middle. So other two sides will be discarded. So since F0 is smaller than F1 and F0 is smaller than F2, so new interval will be new AB basically will be 0.625 and 0.875. Again, you have to divide it equally. So this is your iteration 02 and iteration 03. So A value is 0.625, B value is 0.875. Middle is already known from the previous one, so middle will be basically same as before, 0.75. So you can try writing it up. So 0.75, call this one as x0. So the middle of these two will be 0.6875, which is our x1, and x2 is basically 0.8125. 0.8125. So x0, x1, x0, x2, write the values 0.6875, 0.75, and 0.8125, corresponding values F1, F0, and F2 is basically minus 0.5589594 minus 0.5625 minus 0.558594. So these two are actually equal. So we are at the middle. Uh, and since this is the scenario, we can say that our next interval will be basically 0.6875 and 0.8125. Okay. So, but we calculated that we have to go up to 7 experiment, which is already achieved. Because in the first one we have 3, then the second one 2, then the 2. So we can say that our x optimum here is the middle point, 0.75, and correspondingly f optimum is minus 0.5625. Okay, so this is the method of interval halving. So, and which is even simpler than your dichotomous search. Okay, so in the next class, we'll try to see few more methods related to the one-dimensional minimization methods. Elimination ones, and then we'll go for the interpolation ones, inshallah. Assalamu alaikum.